Alright, so I wanted to make a quick recording for those of you who are out on Friday. Basically, we discussed the mathematics behind the harmonics. Remember when we did the demonstrations, we had the slinky down on the ground, and for certain frequencies I could set up a standing wave for that length of slinky, not for every frequency. And then I told you we would figure out what the math was behind it, and that's what the goal is today. And so basically, we're going to think about how harmonics relate mathematically to all different kinds of instruments. And in order to do that, we're going to analyze them by breaking them up into a few different categories. And so if you think about all the instruments you're familiar with, they can kind of, for the most part, break down into a few small groups. And the first that you're most familiar with, a guitar, a piano, violin, are string instruments, and those string instruments are fixed at both ends. And so we can picture, this is of course the slinky that we did in class. We can picture a length of string of length L that is fixed at both ends. And by definition, if the medium is fixed at both ends, then when I create a standing wave, those are going to have to be nodes because the medium is not moving. And so imagine the very first frequency that set up a standing wave looked like what? Well, it looks like that, and had an antinode in the middle where the amplitude was much greater than each individual wave because it was constantly constructively interfering with its own reflection. And so this is what we call the fundamental frequency, or the first harmonic. And I can do some math. Sorry, that was just a quick parenthetical. As you get ready to do your experiment, formal write-up, the speed of sound at atmospheric pressure is 330 meters per second. And then you have to add 0.6 meters per second for every degree Celsius above zero, and so that's why we were careful to take a record of the temperature in the room when you did your experiment. So that's just a note that I brought up related to the formal report. But in terms of this fundamental frequency, we're looking for a relationship between the length of the string L and the wavelength of this wave that we've created a standing wave of. And of course you can anticipate here, if you imagine that being a crest, then alternatively it's going to alternate between being a crest and a trough. And so we're only seeing half the wave, and so the wavelength for this frequency is double this. And so this length L is half a wavelength for this frequency. And so then we increase the frequency and we lose that standing wave on this length of string until we get to what we call the second harmonic. And the next frequency that produces a standing wave, you can imagine, and you remember from our demonstration, we'll add a node in the middle. And so it'll look like this, and that's what we call the second harmonic. And in terms of expressing L as an expression of wavelength, you can see that this length of L equals the wavelength of the wave. And I've just labeled the new node in the middle and the corresponding antinodes on each side. And of course, again, the dotted line just represents the alternate position, so it's going to oscillate back and forth between the solid line and the dotted line, and that's why at N it's not moving. And then of course the next frequency for this scenario is going to add another node, and it's going to look like this, and two nodes in the middle in addition to the two nodes on the end, a total of 3 antinodes, the so-called third harmonic. And then, of course, the length is 1.5 wavelengths, or 3 halves. And then you'll notice all these expressions I've rewritten in terms of fourths, which you'll see why that's helpful in just a minute. Then, of course, the fourth harmonic is going to add another half wavelength. You're noticing that trend. And I just separated these to make the picture clearer as I did the next one, which looks like that. And of course, how does length relate to wavelength on this one? Well, the length L is double the wavelength, or 8 fourths. And so then I just relabeled everything. The fundamental frequency, where the length of the string is half the wavelength. The second harmonic, where the wavelength is the length of the string. Third harmonic, which the length of the string is 1.5 wavelengths. And the fourth harmonic, where it's double the wavelength. And then we have other terms for these. We're going to call the second harmonic the first overtone, and the third harmonic the second overtone, and the fourth harmonic the third overtone. And you may have noticed this when you did your experiment, right? You got the fundamental frequency, but some of you came across the overtones, and that was that higher frequency that was softer in intensity, but at a shorter wavelength. And if you weren't careful, you accidentally graphed that instead of the fundamental frequency. And actually, what's kind of cool is that these combinations of overtones, and the more complex the musical instrument, the more overtones we get. And it's the combination of adding the fundamental frequency to the overtones that give instruments their distinct sound. And you'll recall we talked about last time that we give that quantity an expression called timbre, and that's the wave shape. And we only looked at a couple of real simple wave shapes, sine versus sawtooth versus square. But in musical instruments, they get very complicated because it's fundamental frequency plus several overtones, and you end up getting wave shapes like these. And so you might imagine the top one might be the timbre or the wave shape for a violin, and then a piano and a guitar or whatever. Notice again, same period, same frequency, same pitch, same amplitude, same volume, same intensity, but you'll hear very different sounds as a result of the very different wave shapes. All right, so then we get to the second classification or second category of instruments, and that would be your woodwind instruments, and this is the one you did the experiment on, right? In the experiment, you had a tube that was opened at one end and closed at the other. As a result of one end being closed, that closed end is going to have to by necessity be a node, and the open end then is going to be an antinode. And if you try and draw a wave that has a node at one end and an antinode at the other, the very longest wave, right, the lowest frequency you can draw for that will look like that. And what is the part of a wavelength that's equal to the length of this open tube? Well, it's 1/4. And that shouldn't surprise you one bit, because in your experiment, when you're using the PVC pipe and the water, which closed it at one end and the other end was open, and we tried to find the shortest possible wavelength to create a standing wave, or excuse me, we moved the column and made the column as small as possible before we get our first standing wave. This is what we got. And that's why you took all your numbers and multiplied them by 4 for the column of air to get the wavelength of the sound. And then, of course, you can imagine there'd be a higher frequency that could also set up a standing wave on this same length of a column of air. You'd add a node, but it's still got an end and an antinode, so it looks like this. So an additional node in the middle, and an additional antinode, and that would be what we call the second harmonic. And looking at the length, you can see that that's going to be 3/4 of a wavelength. The next subsequent wave, it's going to add another node. It's got to end at an antinode, though, because it's open at one end. And so the third harmonic looks like that. And if we did the math, I'll actually do the math in a second when there's a little more space. There's the fourth harmonic. And so here's the math for the third and fourth harmonics. Notice for the third harmonic it's 5/4, and for the fourth harmonic it's 7/4. And so again, we have our fundamental frequency, which is the first harmonic. We have the second harmonic, also known as the first overtone, the third harmonic, also known as the second overtone, and the fourth harmonic, also known as the third overtone. And now you can see why I wrote it as fourths. For the string closed at both ends, then the frequencies were every half wavelength, but starting with the even fourths, so 2/4, 4/4, 6/4, and so on. And open at one end is going to be the odd fourths, 1/4, 3/4, 5/4, and 7/4. And so that's a shortcut you can remember to help make sure you keep yourself straight, but also make sure that you know how to go back and actually reproduce the math by imagining the various standing waves. And so then here's the last possible scenario, and I couldn't think of any musical instruments that are actually physically like this, other than those whistling tubes that you swing above your head. If you have a tube that's open at both ends, then the very first wave that can create a standing wave has to have antinodes at both ends, so it has to have one node in the middle. And you can do the math for yourself to see that that is identical to a string fixed at both ends, right? If you have a node at both ends and an antinode in the middle, then mathematically it's going to be the same as two antinodes at the end and a node in the middle. And so you'll see it's going to be the exact same. It's going to have the even fourths, so 2/4, 4/4, 6/4, and 8/4. And then here's just an example of a type of question I might ask. And so I might ask if there's a string fixed at both ends and the string is 1/2 meter long, standing waves of which of the possible wavelengths, following wavelengths are possible. And so 1 meter, 0.75 meters, 0.5 meters, and 0.25 meters. And then I'm anticipating that instead of asking which of these wavelengths are possible, I could have also asked which frequencies will resonate. And all that would do is add an extra step using the equation you're familiar with of wave speed equals wavelength times frequency. You convert the frequencies into wavelengths using the speed of the wave, probably sound, and it'll be given, to then solve for the wavelengths. And then you have the question that I asked here, which is that wavelength going to set up a standing wave on that length of string? And so how I'm going to do it is I'm going to say, well, the first scenario, the wavelength is 1 meter and the length of the string is 1/2 meter. I'm going to rewrite it in the way that I had the other expressions from the previous math and say L equals lambda over x. Well, in this situation, what is x? It's 2. And so is lambda over 2 equal to L one of the standing waves on a string fixed at both ends? And the answer is yes. Of course, that's the first harmonic, the fundamental frequency. And then I could go to the next one, which is 0.75, and I do the same thing. I rewrite it in terms of the expressions that we've already done, and then solve for x. Well, in this case, x is 3/2, which means L equals 2/3 lambda. Does that fit to one of the standing waves on a string fixed at both ends? And the answer is no. And so 0.75 as a wavelength, or again, if I gave you the frequency, which would just be that divided by the speed divided by that. So if I say the speed, it sounds 340 divided by 0.75. If I give you that frequency cannot set up a standing wave on a string fixed at both ends if the string is 0.5 meters long. And so these are kinds of questions we'll ask. And again, the 0.5, we do the same thing. Well, if they're equal, then x is 1. And is that one of the scenarios? Yes, of course, that was the second harmonic, right? And then so on and so forth. And so these are the types of questions we can ask, and this is the math behind the harmonics of the different types of musical instruments.